Hi, I'm Mike Moreau, NASA's Deputy Project Manager for the OSIRIS-REx mission.
And I'm Coralie Adam, the OSIRIS-REx Optical Navigation Lead and Tag Navigation Manager at KinetX Aerospace.
This is Bennu, or rather, a model of Bennu constructed from imagery and LiDAR data recorded by the OSIRIS-REx spacecraft, which spent most of 2019 flying in close proximity to Bennu, observing it in unprecedented detail. The incredibly rocky surface you see before you was a big surprise for our team. We're going to talk to you about the challenges our team had to overcome and share some of the results from the successful tag at Bennu on October 2020. The sample collection technique used by OSIRIS-REx is called touch-and-go, or tag for short. And I'm going to talk to you about how tag works. You're watching a simulation that shows a view of Bennu from the perspective of the spacecraft as it sits in orbit about 1 kilometer above the surface of Bennu at the start of the tag sequence. The whole tag sequence is about 4 hours, but we're going to have it compressed into about 2 minutes here. Tag begins with a thruster burn that causes the spacecraft to depart orbit and head out over the sunlit side of Bennu towards the tag site. A sample collection mechanism called TAG-SAM is deployed at the end of a 3-meter-long robotic arm. TAG-SAM is the only part of the spacecraft that will touch the surface during tag. As the spacecraft transits out over the sunlit side of Bennu, it begins snapping images with the navigation camera and processing those images to autonomously update its location relative to Bennu. The dramatic rocky terrain the spacecraft is flying over meant that there were very few locations on the surface feasible for navigating the spacecraft into. One challenge was simply how to pick the best sample collection site, since none of the candidates met our original specifications. As the spacecraft reaches the region of the tag site, it computes updates to the final 2 maneuvers that will target the desired contact point in the center of the Nightingale site, which you can just see coming into view at the upper right of the image right now. The first of these maneuvers is the checkpoint burn. It was performed at about 100 meters above the surface and starts the spacecraft on a descent to Nightingale. About 10 minutes later, once the spacecraft has reached an altitude of about 60 meters above the surface, the match point burn is conducted. Match point slows the descent of the spacecraft and matches the horizontal velocity with the rotating surface below. All the while, the spacecraft is descending the surface at about 10 centimeters per second and is calculating its predicted contact point with the surface. When an accelerometer detects contact, a nitrogen gas bottle is fired, and the thrusters on the spacecraft then fire shortly thereafter, taking the spacecraft away to safety. When the TAG-SAM comes into contact and the gas bottle fires, it stirs up material under the head of the TAG-SAM, forcing some of that material to be driven up into the containment mechanism. The TAG-SAM is only in contact with the surface for just a few seconds before the spacecraft is backing away to safety. Now, the spacecraft was originally designed to contact the surface within 25 meters of the desired tag location, but it would have to perform much better than that in order to successfully collect a sample at Nightingale. And Coralie is going to talk about how we overcame some of those challenges.
So here's a top-down rendering of the Nightingale sample site. You'll first see a yellow circle representing that 25-meter radius ellipse that the mission was originally designed to tag into. Nightingale is 10 times smaller in area, only 8 meters across, or a few parking spaces wide. It's surrounded by boulders, one in the upper right-hand corner as tall as a 2-story building. To safely and accurately get the spacecraft into this site, the OSIRIS-REx mission team had to redesign several aspects of TAG to overcome these challenges. One major change to TAG was the onboard algorithm for those final 4 hours of autonomous descent to the surface. The mission had to pivot from the original LiDAR-based guidance design to a much more accurate but more complex vision navigation approach called natural feature tracking. A catalog of features, or digital terrain maps, was built from high-resolution images and altimetry data and uploaded to the spacecraft. After orbit departure, NFT begins taking images of the surface every few minutes and identifying the locations of these cataloged features in the images. This allows the navigation system to solve for the position and velocity of the spacecraft, which enables it to recompute the updates to the checkpoint and the match point burns that get the spacecraft down to the surface. Another challenging aspect of TAG was that the site is littered with and surrounded with large hazardous rocks that could threaten the safety of the spacecraft. The mission addressed this by adding a hazard map check evaluated just about a minute before contact, about 5 meters above the surface. Before TAG, we estimated a 6% chance of a low altitude abort occurring at 5 meters based on our hazard map, which luckily wasn't realized and the spacecraft successfully made contact on the first attempt. With that, I'll pass it back to Mike to show you some of the amazing videos from TAG.
Okay, so the sequence of images that you're seeing now were recorded by the SAMCAM from starting about 40 meters above the surface until through contact and until about 20 seconds after contact. You can see the TAG-SAM arm in the center of the field of view. A few minutes before contact, you see the TAG-SAM move as the wrist is powered on to move it into position for TAG. And then about a second after contact, the gas bottle fires, and that's sort of when all heck breaks loose in the field of view. So all indications from this imagery are that the TAG event went off flawlessly, that the head touched the surface flush, and that we probably got a lot of great sample material. But I'm going to talk about what happened in a little bit more detail on this next chart. You can see on the left side, I'm just showing 2 frames from that previous sequence, the image just before contact, and then the next one just after contact, but before the gas bottle fired. So one of the first things you can take away from this is that the head has penetrated into the surface maybe 4 to 5 centimeters before the gas bottle fired. That's great news because it means that the TAG-SAM is preloaded with material before the gas bottle even goes off, really increasing the chances of getting some good material captured. You can also see how the TAG-SAM is interacting with the surface. On the left side of the image, you can see this rigid boulder or rock that's cantilevered up as the head presses into the surface. You can also see what looks like a rock just at the top of the head before contact. As soon as the head touches it, it just turns to dust. And that's great news because that dusty material is just the kind of thing that the TAG-SAM was designed to collect. So anyway, this is really positive indications right from the start that we got a good sample. Now on the right side, I'm going to talk about the sequence of events. I mentioned that the gas bottle firing happened about 1 second after contact. Well, the arm continued to descend into the surface for another 6 seconds before the thrusters began to fire for the back away. The forward velocity continued for another 3 seconds after that until about 9 seconds after contact before the velocity reversed and the spacecraft started to lift off again. And then it wasn't until 16 seconds after contact that the TAG-SAM head rose above the original surface of the asteroid. So all in all, the spacecraft descended about a half a meter. The head of the TAG-SAM was about a half a meter below the original surface, and the contact point was less than 1 meter away from the targeted location.
So here's another view of TAG from the wide field of view navigation camera that is off-pointed from the arm by about 15 degrees. So you won't see the arm, it's just outside of the top of the field of view. You see the Nightingale crater coming into the frame, and soon you'll see the shadow of the arm right before it makes contact with the surface. We have contact, we begin backing away, see lots of debris, and as we are, the spacecraft is elevating above the debris cloud, you can see banning across the frame a large plume of lofted material that is moving above the surface. So now I'm going to slow that down a little bit and talk about it in a little bit more detail. So as you start to see this plume of material rising up, and you see a dark shadowed region in the lower left-hand corner. That is the shadow from the plume that is painting its way across the surface in the bottom left-hand corner of the frame. So TAG clearly generated a lot of debris that was elevated from the surface. And it was such a smashing success that we actually packed the head so full that it couldn't close due to large rocks wedging the mylar open and causing small material to leak out. The team quickly determined there was more than enough material in the head to meet the requirement, and stow was conducted flawlessly on an accelerated timeline. Here you see the sample return capsule closing, tucking the sample in for protected re-entry into Earth's atmosphere. Now, a few months after TAG, we sent the spacecraft back to Bennu for one final look at the Nightingale site to see what it looked like after the dust had settled. Here you can see dramatic change. The rocks have been rearranged entirely. There is new, darker material scattered throughout the site. We see about 100 square meters of surface that's been disrupted and changed by TAG, a campfire ring of boulders, and the center of the image here is basically, center of the crater is where we actually made contact, although the thruster plumes affected much more of the site as the spacecraft backed away after TAG.
So after more than 2 years of really intense operations around Bennu, in May of 2021, the spacecraft performed a burn on its main engine thrusters to depart the vicinity of Bennu and set up a rendezvous with the Earth in 2023. The team is targeting September 24th of 2023 for the release of the sample return capsule, the only part of the spacecraft that will return to Earth. The SRC will enter the Earth's atmosphere over the western United States and parachute to a landing within the Utah Test and Training Range near Hill Air Force Base. Ground crews will recover the SRC, transport the sample canister to NASA's curation facility at the Johnson Space Center, and a portion of the sample will be studied by teams of scientists all over the United States and all over the world. However, a large fraction will be archived for study in by future generations. Indications are that we successfully collected between 100 to 200 grams of pristine carbonaceous asteroid regolith, material that is unique when compared to the existing meteorite collection. We expect more surprises from Bennu as this material is studied in detail in the coming years.